minus 40 degrees Celsius. That's not a lab test. That's the temperature of a Siberian freight corridor in January. The kind of cold that drains lithium batteries, cracks diesel fuel lines, and stops logistics operations dead. FAW just drove a sodium-ion truck through 15,000 kilometers of exactly that. 90 Fancham battery capacity, fully recharged in 20 minutes. 8,000 charge cycles under constant fast charging. Every expert who said sodium-ion could never power commercial trucks just ran out of arguments. This is what the end of diesel actually looks like. Let's be honest about something the EV industry doesn't like to admit. Electrifying passenger cars is hard. Electrifying heavy-duty trucks is a completely different category of difficult. A long-haul diesel truck can refuel in under 10 minutes, carry enough energy to run 1,000 kilometers, and operate at minus 30 degrees Celsius in the middle of a Siberian winter without missing a beat. For decades, battery technology simply could not compete with that equation, and the trucking industry knew it. The core problem wasn't just energy density. It was a cluster of interconnected failures that compounded each other in brutal conditions. Standard lithium-ion batteries lose significant capacity in extreme cold. LFP, lithium iron phosphate, the chemistry that became the workhorse of the EV industry, degrades sharply below minus 20 degrees Celsius. At minus 30 or minus 40, you are not losing 10 Fancham of your range. You are potentially losing 30 to 40 Fancham of usable capacity. For a passenger car, that is inconvenient. For a commercial truck hauling cargo across northeastern China, Scandinavia, or the Russian steppe in January, that is operationally catastrophic. Then there is charging speed. Diesel takes 10 minutes. Early electric truck charging took hours. Even improved lithium systems struggled to deliver the kind of ultra-fast recharge that commercial logistics operations demand. And underneath all of this sat a quieter problem: cycle life. Fast charging destroys lithium batteries faster. The harder you push them, the fewer total charge cycles you get. For a trucking fleet running vehicles 300 days a year, battery longevity directly translates into total cost of ownership, and the numbers, until recently, were not good enough. This is the wall that sodium-ion technology just walked straight through. Sodium-ion batteries are not a new idea. The chemistry has been understood for decades, but for most of that time, the energy density was too low, the manufacturing processes too immature, and the cost advantages too marginal to justify commercial deployment. Then something shifted. Chinese battery manufacturers, particularly companies like CATL and the more specialized sodium-focused firm Hina, began solving the cathode and anode material problems that had held sodium-ion back. Hina, which holds patents across cathode materials, anode materials, and manufacturing processes, has pushed sodium-ion energy density to 165 watt-hours per kilogram. That number deserves context. 165 V is not record-breaking. It is roughly equivalent to the current generation of BYD blade battery cells, the same chemistry going into mass-market EVs that millions of people are buying right now. In other words, sodium-ion has reached parity with proven, commercially deployed lithium technology on energy density. But sodium-ion does something lithium fundamentally cannot. Sodium ions are larger and heavier than lithium ions, which sounds like a disadvantage. In one specific way, it is. Energy density will likely always trail lithium at the cell level, but that same electrochemical property makes sodium-ion dramatically more stable at temperature extremes. The ionic behavior does not collapse in the cold the way lithium chemistry does. The internal resistance doesn't spike. The available capacity doesn't crater. This is not a marginal improvement. This is a structural chemical advantage that becomes more significant the colder the operating environment gets. And FAW just proved it holds up across 15,000 real kilometers. FAW, one of China's largest and oldest commercial vehicle manufacturers, fitted one of their heavy-duty trucks with a 340 kilowatt-hour sodium-ion battery pack. To put that in perspective, a Tesla Semi uses roughly 860 kilowatt. A typical electric passenger car uses 60 to 100 kilowatt-hour. 340 kilowatt-hour is a serious purpose-built commercial energy storage system. They ran this truck for 15,000 kilometers, not in a laboratory, not in a controlled climate chamber, in real operating conditions. The headline result, at minus 40 degrees Celsius, the kind of temperature recorded on high-altitude mountain passes during winter storms, the battery retained more than 90 Fancham of its usable capacity. Read that again. Minus 40, 90% capacity retention. For comparison, LFP batteries tested at -30 degrees Celsius in independent studies have shown usable capacity retention dropping to 60 to 70 FAW, depending on the discharge rate and thermal management quality. At -40, that number gets worse. The sodium-ion pack didn't flinch. Now look at the charging data. A 340 kilo battery charged in 20 to 25 minutes. Working backwards from those figures, the average charging rate across that session had to have been well above 500 kilowatts, and peak rates likely approached 700 kilowatts. That is not a theoretical specification written in a product brochure. That is a charging event that happened on a real truck, measured during a 15,000-kilometer test program. For the trucking industry, that number is transformative. A driver pulls in for a mandatory rest break. 30 minutes later, legally required downtime that was going to happen regardless. The truck is fully charged. Not 80 FAW, fully charged. The operational penalty of switching from diesel to electric effectively disappears. But the most underreported number from this test is the cycle life figure. More than 8,000 full charge cycles under fast charging conditions. That is double the cycle life of standard LFP batteries under similar fast charging stress. For a fleet operator calculating total cost of ownership across a vehicle's working life, doubling the battery's functional lifespan is not a minor footnote. It potentially changes the entire financial model of electric truck operation. This is not one company running an interesting experiment. This is the leading edge of a coordinated industrial strategy. 11 Chinese government ministries, including the Ministry of Transport and the National Development and Reform Commission, jointly released an implementation framework for scaling new energy-heavy trucks across China's commercial fleet. The policy sets a specific binding target. By 2030, electric trucks must represent 40 FAW of annual new truck sales, with the total electric fleet exceeding 1.6 million units. More significantly, the target calls for 20 FAW of all heavy-duty trucks on Chinese roads to be electric by 2030, not just 20 FAW of new sales, but 20 FAW of the entire active fleet. That is an enormous number. China operates one of the largest commercial trucking fleets on the planet. Converting 20 FAW of it to electric within 5 years requires not just viable technology. It requires that the technology be cost-competitive, operationally reliable, and available at massive manufacturing scale. The sodium-ion pathway addresses several of the cost barriers that made electrification difficult. Sodium is one of the most abundant elements on Earth. It does not require cobalt. It does not depend on the lithium supply chains that have created geopolitical tension and price volatility over the past decade. The raw material cost floor for sodium-ion cells is structurally lower than lithium-ion, and that gap only becomes more meaningful as production scales. Chinese diesel trucks operating in urban environments have been among the most significant sources of particulate pollution in the country for decades. The government's urgency here is not purely economic. The public health calculus is also driving the timeline. 2 years ago, the consensus view across most of the battery industry was clear. Sodium-ion was interesting chemistry for stationary storage, maybe useful for low-cost urban EVs, but fundamentally unsuited for demanding commercial applications. That consensus is now broken. 15,000-kilometer test didn't just validate sodium-ion for cold-weather trucking. It demonstrated that the technology performs better than lithium alternatives in exactly the conditions where trucking is hardest: extreme cold, heavy loads, and high-frequency fast charging. The companies that will feel this shift first are not the ones in China. China's fleet is already converting. The pressure will arrive in Scandinavia, in Northern Europe, in the freight corridors of Northern Asia, wherever diesel trucks currently operate in brutal winter conditions, and the economics of lithium battery electrification never quite penciled out. Sodium-ion doesn't need to be perfect. It just needs to be better than diesel in the conditions that matter most. In -40 degrees Celsius, across 15,000 kilometers, it already proved that it is. The disruption of heavy trucking has officially begun.